Good afternoon, everybody. Welcome to the final lecture of the Introduction to Data-Centric AI IAP class. Today we'll be talking about this really exciting topic of data privacy and security. And in general, the topic of ML security is really hot these days. It's an interesting and very active area of research. So I plan to touch on a bunch of topics from that area in this lecture, in addition to focusing on a particular set of attacks that we'll cover that are very data-centric. Just out of curiosity, who here has taken a security class before? Show of hands. Nobody. Interesting. Okay. Well, good thing I planned on covering all the relevant security background in this lecture. And please ask me lots of questions as I go through this material. All right, so to dive right into things, we've been studying data and machine learning models, and machine learning models are sometimes trained on sensitive data, right? A lot of really interesting applications might involve, say, training a machine learning model on something like a healthcare data set. And then after a model is trained on a sensitive data set, like what happens with the model after that? The model will be deployed in some way or used in some way, right? And a couple common scenarios include models just being released publicly, like someone might train a machine learning model on a sensitive data set and then just post the model on the internet. Or another thing that might happen is somebody trains a machine learning model on a sensitive data set and then makes the model available as an API. So rather than releasing the model's architecture and weights directly to the public, they'll just have a web API endpoint where people can upload inputs to the model and just receive the outputs. So it's available in this black box way, but publicly available so anybody can feed inputs to the model and observe its outputs. So when training ML models on sensitive data, a reasonable question to ask is whether the model leaks sensitive information about the data on which it was trained. Like the whole point of the machine learning model is to learn characteristics about the data set over which it's being trained, right? So if there's sensitive data input to the model or to the model training procedure, it's reasonable to think that the model itself might be influenced in a kind of bad way by that sensitive data. And so related to that, there are a couple attacks on machine learning models that arise that we'll cover in this lecture. One of them is a membership inference attack. So it turns out that in certain cases with certain machine learning models, just given the model, it's possible to, now given a fresh data point, infer whether or not that data point was used as part of training that model. Like given a data point, was this data point used in the training set of the model? So can anybody think of an example scenario where the existence of this kind of an attack might be problematic? Like, why might it be problematic if somebody could infer whether a data point was in a model's training set? Like, can you think of a situation in which just the mere presence of a data point in a training set like implies something sensitive about that data point? Yeah?
If you fed in the input in the training set, then it would have maybe high confidence in whatever the output would be, and so maybe you would get that sensitive information back.
Yeah, so I think what you said is correct. It's not exactly answering my question. It's kind of looking ahead at how you might attack models and actually figure out whether a data point's in the training set or not. So we'll cover that a little bit later in the lecture. Yeah.
For models trained for medical purposes, and they would use a certain population have this kind of disease, which is confidential information.
Yeah, that's a great example. So machine learning models trained on medical data sets. It might be that the data set consists only of patients that have a certain medical problem. And so just being able to figure out that a particular patient belongs to that data set reveals that sensitive information about them, right? Perhaps I have some particular medical condition. Now you can just do the membership inference attack given Anish in the model, and then if Anish appears in the model's training set, now you know that I have this sensitive medical condition. Yeah, that's a great example. So that's one type of attack we'll cover in this lecture, membership inference attacks. And then another type of attack we'll cover is something called a data extraction attack. And just from its name, you might be able to guess what that means. The idea is that just given a trained machine learning model, you might be able to extract just kind of raw training data from the model itself. These models sometimes memorize portions of their training data, and so you can just pick that out of the model. And there's a lot of other types of attacks on data and on machine learning models. There's some links in the lecture notes if you're interested in those, but I won't cover those today because there's just way too much to cover. And there are thousands and thousands of research papers on this topic of machine learning security. So before we get into specific attacks and attack algorithms and things like that, let's start with some security preliminaries. Like, we need to be able to answer the question of, like, what does it mean for a model to be secure, or what does it mean for a system to be secure? It's like, how do we define security? And so a framework we commonly use involves describing a security goal. Okay, so we have some system, like what should and shouldn't happen with the system. And another piece of this is something called a threat model. And what this threat model does is it constrains an adversary. So we have some system, there's some idea of what it should and shouldn't do. So security goals, what the system is trying to accomplish. And then the threat model constrains the adversary. So like, what can and can't the adversary do? What does the adversary know? What does the adversary not know? Maybe things like how much computing power the adversary has, things like that. Now, these sound kind of abstract. We'll go through a bunch of concrete examples, and then this will make a lot more sense. But only once you define these sorts of things can you even talk about whether or not a system is secure. So before we kind of finish defining security, let's go through a couple examples of just real systems and go through an exercise of threat modeling. Let's think about what the system is trying to accomplish in terms of security goals and what kind of an adversary system or its associated security setup is trying to handle. Let's start with an image prediction API. Perhaps some of you have used something like this. There are lots of cloud services that make available an API where you can feed in an image and get back a prediction. So you might feed in a picture of a person to this model that lives in the cloud, and then this outputs something like person 97% and dog 2%, cat 1%. So input image, model that lives in the cloud, and then you get back a set of predictions, basically a probability distribution over all the different classes that this classifier can predict. All right, so this is the system we're talking about here. Pretend this is, say, something like Google Cloud Vision API. Now, what properties might the cloud provider want from this model in terms of like security-related things it should accomplish, or like things that should or shouldn't happen with this API? Any ideas?
Some particular person, you should just be able to say person. I don't know how possible it is to break that part of it, but it should be constrained to just the outputs that are defined.
Sure, so the system might be set up so that there's a particular set of possible class labels, and it shouldn't be possible to tweak the input image such that you get some output that's not in that class. So for example, maybe you just want to say person, but it shouldn't identify specific people. I'll give you another particular security goal that a cloud provider might have in mind. The cloud provider might want it to be the case that it's not possible for somebody interacting with the system to figure out what the model's parameters are, right? Like Google spent a lot of money collecting a big data set and training this model. It'd be a shame if somebody could just extract the model and then run it locally instead of paying Google a penny every time they feed a data point into there, right? So in this particular example, let's say that the adversary wants to protect the model's parameters. So the model's parameters should be kept secret. for this particular example, the threat model, like what we say about what an adversary can and can't do is, I think, the more interesting part. So if someone's trying to build a secure system, who's trying to accomplish this security goal, would it be reasonable to consider, for example, an adversary that can hack into the machine that's hosting the model and run arbitrary shell commands on that machine? That's not really a useful constraint on the adversary, right? Like the system, that's not really realistic, or maybe we don't care about that particular type of attack. And if we allowed an adversary to do something like that, well, then we can't accomplish the security goal, right? But what are some things that people should be able to do with this model and yet not be able to extract the model's parameters? Okay, this is an image prediction API. Users, and therefore the adversary, can certainly just feed data into it and observe the outputs, right? Like the adversary is allowed to make queries to the model. So I'm just going to list some things that the adversary can and can't do. This is not going to be a complete list. Can make queries. And we can expand on this a little bit. Maybe, and if you think about like normal users, they're probably just taking pictures with their phone or something and feeding those images into the model. But the way this model's set up, maybe it accepts arbitrary JPEG files. And if an adversary is trying to do something funny, like they can make arbitrary queries. They don't have to take like natural images. They can take, they can basically construct whatever funny image they want. They can set the color of each individual pixel and feed it into the model and see what happens. Like that is an action that the adversary is allowed to take. And it should be the case that even if we allow an adversary to do that sort of thing, it shouldn't be possible to extract model parameters. So are we getting a flavor of what security goals and threat models look like? You can keep expanding on this. What is something else reasonable that we might expect an adversary to be able to do? We're just kind of making stuff up here because like we're not a cloud provider. We don't have all the information here. So we're just kind of imagining what a cloud provider might go through when doing threat modeling in a scenario like this.
If it's online, you can inspect whatever server requests the site is making and possibly extract some meta information.
Yeah, sure. So if this model is hosted online, you can open up the network inspector in your web browser and see what are the actual HTTP requests being made to the model, and maybe there's some extra metadata in there or something like that. So yeah, all that information would also be available to the adversary. And then here, I'll give you one more thing. We're just making this up again. But we might assume that the adversary actually knows the model architecture. Right, that, and depending on the scenario, may or may not be a reasonable assumption, but a lot of times these cloud providers, like they're doing research, developing fancy new machine learning models that get state-of-the-art accuracy on these public data sets, and then they go and write research papers about them. So they're telling the world, like, oh, this is what model architecture we're using. Now, they don't necessarily provide the trained model. Like maybe that's really expensive to train. They have to collect a big data set and run training for many thousands of GPU hours. But the model architecture itself, like you can just read the latest NeurIPS paper and find out what they're using. So maybe it's the case that the adversary can know the model architecture. And just to make this a little bit more complete, let's think about maybe what are some things that the adversary shouldn't be able to do or can't do, or things that are out of scope. Like if you're trying to design a secure image inference API, what things do you not care about? Like what kinds of adversaries might you not care about? Like what kinds of things might you assume the adversary does not have access to? Okay, so in the setting, the adversary can give an input and look at the output. One thing we might assume is that the adversary is not allowed to look at intermediate activations, like of hidden layers inside the neural network that's being used here, right? All the adversary sees is the final result. So can't see hidden layer activations. Some other things that we might assume. So maybe this image prediction API takes in images like JPEG files. And so the adversary has to feed in valid images. Like if the image just fails to decode, then nothing downstream from the image will run, right? So you might assume that any input to the model is constrained such that every single pixel value is like between 0 and 1, right? So you can't feed in like crazy big values or negative values or things like that and run the rest of the computation, even though maybe that reveals extra information that's useful to an adversary. Just given the system that's set up around this model, you might assume that that's not possible. And there's some other things that might be reasonable to assume. Again, kind of given the system and the context around the model, maybe you can assume that the adversary makes less than 1,000 queries per hour. It's reasonable to implement some kind of basic rate limiting for a model that you deploy. And so any adversary that's trying to break the system is constrained by that. Maybe we can assume some other things like the adversary spends less than like $100,000 to try to break this model. So that's how much compute they can use. Right? And that's also reasonable to assume because like given the system, maybe the cloud provider could say, oh, an adversary could just train their own model if they spent more than this amount of money. So like as long as it costs at least this much to attack our system, like that's good enough. So, any questions so far about this threat modeling exercise? So just giving you a little bit of a flavor of how to think about things in a security-related context. So now going back to this whole definition of security and security goal and threat models, now once we have these pieces, we can define what it means for a system to be secure. And so a system is secure if its security goals are satisfied when in the presence of an adversary that is constrained by the threat model. And this has to hold for any possible adversary. Right? So we're not thinking about like a particular type of attack against the system, and oh, if the system prevents that particular type of attack, then we're good. No, it's this very broad way of defining things. Like you say what an adversary can and can't do, and then you're kind of trying to quantify over all possible attacks, like all reasonable things that somebody might do, where this is the definition of reasonable. Only if a system is secure under all possible adversaries is it secure. Like only then do we call it secure. And that's one of the things that makes security really tricky, right? Like this is a kind of weird thing. In machine learning, normally when we evaluate things like, say, you're evaluating model accuracy, it's very straightforward to do so. Like you're quantifying over all the data points in the data set. So you can just like run the thing on every data point and see how it does. Whereas in security, if you want to reason about whether or not a system is secure, you're quantifying over all possible algorithms. That's like a really weird thing if you're not used to it, right? Like all algorithms that follow some set of constraints that you define. And so that's what makes security really hard. Any questions so far? All right then. Let's do another very quick threat modeling exercise. I won't write on the board for this one, but we can just talk through it because it'll set up the next really interesting thing I want to talk about, which is membership inference attacks. So again, threat modeling exercise just like that. Now instead of an image prediction API, let's suppose that we have a hospital that's trained a machine learning model on a data set of patient records and is trying to do something like, say, predict the likelihood of the patient needing intensive care. Or for this example, it doesn't really matter. The hospital's trained an ML model on patient data and it does something, like output some classification result. One security goal that the hospital might have, like maybe they have this data set that's private, it contains patient information, but they want to train a machine learning model on it and then just release the model to the public. Like make it available for download. Anybody can download like the PyTorch model and model weights and run it locally. And maybe researchers and other hospitals can make use of this thing. So a security goal that the hospital might have is that it shouldn't be possible to infer anything, like identify specific patients or like figure out who were the patients included in the data set that was used to train this model, right? So that's the security goal. Models shouldn't leak information about the patients. And then in threat modeling, the hospital might assume, like, okay, since the hospital is releasing the model online, the adversary has full access to the model. So unlike this scenario where the adversary can only make queries to the model, like feed in inputs, in this new scenario of the hospital and the machine learning model trained on patient data records, the adversary actually has full, what's called white box access to the model. So the adversary can poke at the internals of the model, tweak things if they want. They have full knowledge of the model architecture and the parameters. And there are other things that might be reasonable to assume. Like maybe the hospital assumes that the adversary does not have access to the original data set on which this model was trained. Like that's a reasonable assumption, right? It's like the secret data set belonging to the hospital. But it might be reasonable to assume that the adversary can access a similar data set. Like maybe other hospitals have released de-identified data sets that are kind of similar in shape. So the adversary might have access to like the general data distribution from which the training data set was drawn. So that's under this like threat model of things the adversary can do. And then there are, if we want to list a couple things that an adversary might not be able to do, well, one example is maybe the hospital assumes that the adversary can't obtain any subset of the training set directly from the hospital. So like what's out of scope is somebody just hacking into the hospital servers and like downloading the database. Another thing that, like another kind of subtle example might be, okay, so the hospital is releasing a trained model, but probably the way they trained is like they trained it over a bunch of epochs and maybe they took checkpoints of the model weights while they were training. And even though the hospital is releasing the final trained model, the hospital hasn't released all the intermediate model checkpoints. So the threat model might assume that the adversary does not have access to those intermediate things. And again, the reason it's important to define what an adversary can and can't do is so you can quantify overall possible attacks that satisfy this threat model. And in some cases, like maybe there's an attack that makes use of this information of intermediate model checkpoints. And in this particular case of this hospital example, we might just declare up front, like, okay, we're not interested in those, like the hospital's not releasing that information, and so we don't believe that it's in scope. We don't care about that type of adversary. Any questions so far? All right, let's get into the really exciting stuff then. Let's talk about our first type of attack. So we're going to first cover membership inference attacks. In this type of an attack, we have some data set D that contains data points X, Y. So there's a bunch of these that form a data set. And then we have a model M trained on this data. And then the question is, given some new data point X star, Y star, the idea is to figure out, given this and given access to the model, was X star, Y star included in the model's training set D. Is that setup clear? And at the beginning of the lecture, we talked about what's interesting about this attack, right? We talked about that example of patient data records and how the mere presence of a data record in a data set and being able to infer that can leak sensitive information about the X or about the Y. And even here, I haven't really fully specified like what access to M means. In this particular lecture, we're going to constrain this to black box access. So the attacks that I'm going to talk about actually don't involve peeking inside the internals of the model M or even knowing the architecture or anything like that. All you need to do is be able to feed inputs to the model and observe the final outputs, like the probability distribution over class labels. So yeah, this is the type of attack that we're interested in, and it turns out that it's possible to do this kind of an attack. So I'm going to talk about one algorithm for doing so. That involves something called shadow models. So at a high level, this attack is using machine learning to break machine learning. What's kind of cool, okay, so we have the setting where we have an X and a Y. And what we can do is we can take our model M and feed this X into the model to get, here, maybe I'll draw like a, we can feed our X into the model, not look at its internals, but get the final output, right? Like a vector of probabilities. And what the shadow models attack does is it's going to train an attack model A that takes as input the output of the model, and also the original label, and then tries to guess like yes or no for this like x, y in D question. That's the overall setup. So I haven't talked about how you actually construct this thing, but does this setup make sense? It's like use machine learning to break machine learning. We're going to train a model to answer the question we're interested in answering. And so in the shadow models attack, we're going to train this model A in a supervised manner. So how would we do supervised learning on this if we don't actually have, like we don't have the labels, the yes, no is a data point in this training distribution or training data set D. We don't actually have those labels, right? Like the whole point is to figure out, of this attack is to figure out if a particular data point was in the training data set. The attacker doesn't have access to the training data set. Yeah.
Could you share like an example, for example, security or medical application and why this is like really important?
We went through that at the beginning of the lecture. Were you? Yeah. Yeah.
Can you explain the architecture of the shadow model?
Yeah, so I actually haven't talked about what shadow models are yet. Was the question, what is the architecture of A?
Yeah, I don't understand like why this there.
Yeah, okay, let me just explain the whole picture again. Okay, so the setup is, okay, we have some new data point, maybe I should write stars next to those. As the attacker, we have some data point xy, or I'll say x star, y star. Right, so at attack time, we're given this data point, and then what we're going to do is feed in this data point to the model and get the prediction vector out. And that's really the only thing we can do, right? With black box access to the model, all we can do is feed in inputs and look at outputs. And then what we're going to do is we're going to train a new model, an attack model A, that takes in this prediction vector and also the original label, since we have that information, or like the true label of the data point. And then it tries to figure out, so it's a binary classifier, and it says like yes or no. Does this model believe that this data point came from the training set that this model was trained on? Does that answer the question? Yeah. So that's the overall setup. And now the question is, how do we actually construct this model A? And I said we're going to construct it using supervised learning. But now, how do we get the training data set for that model? And so the idea with shadow models is to basically make use of some extra information. The idea is that oftentimes an attacker, even if they don't have access to the original training data set D, they can construct some new data set, let's call it D prime. So you'll get data set D prime that has a bunch of data points in it that kind of look like the stuff in D. And in practice, this can be like, maybe if you're working with patient medical records, you have no idea what data set that a hospital trained their machine learning model on, but you can just go on Kaggle or something, or there are a bunch of hospitals that release de-identified patient information online. And so you can get stuff that looks like pretty realistic and just use that to construct some new data set D prime. And the next thing is partition this into two data sets. We'll call it D prime in and D prime out. And so by partition, it's like each data point in here either goes into this bucket or this bucket. Okay, so now we have two data sets. And then what we can do is guess a model architecture. And then train a shadow model. We'll call that M shadow. So I'm just going to make up some machine learning model architecture and then train that on this data set D in. Okay? So I'm kind of doing like what the hospital did. I'm training a model on a data set. And now, does anybody see where I'm going with this? What can I do next? So now I have a data set where I have a model and I have a data set. I have access to the ground truth of what data points the model was trained on. And so now I can collect or construct the training data set for my model A by doing, okay, so what I can do is I can, for each data point x, y in Dn, I can calculate my shadow model's output on x. And then I can add to this new data set I'm constructing. I'll call it dA for the data set that's going to be used to train model A. I'm going to add to this data set the data point y bar, y, yes. And then I'm going to do the same thing for x, y in d out. Give to my shadow model this x to get some y, and then add to dA this new synthesized data point, y, no. All right, so now I have this new data set dA that consists of prediction vectors and class labels and whether or not this thing was used in training the model. So then after that, the rest of the attack is pretty easy. I can train this attack model A on this new data set that I just constructed, dA. And yeah, there's a lot of things you can choose here. Like you can choose the architecture of the shadow model. You can choose the architecture of A. Pretty simple choices work for A. You kind of have to just play around with things to see exactly what ends up working well in practice. Like for your shadow model, you probably want to guess an architecture that's similar to the original model that was used by the victim. Whereas for A, like pretty simple models work out. So then once we have A, we're basically done. We perform the attack, which is already drawn in that picture up there. Yeah, question?
How to verify the results of model A is impossible. That's your best guess.
Yeah. So the observation was that to verify the output of model A at evaluation time is impossible. Like it's just your best guess. Is that what you're saying? Yeah. So that's absolutely right. Like when you're trying to attack the hospital and figure out if a data point appears in the hospital's data set or not, well, like you don't have access to the ground truth. So this is the best you can do. In a research setting or where you're trying to evaluate the effectiveness of the attack, you can go through this whole process, starting with creating the original data set yourself, and there you will have access to the ground truth, right? Like you're the one training that first model. And so in that case, then you can actually evaluate the efficacy of this attack. And so that's the setting we have for you in the lab for today's lecture. So the lab is all about membership inference attacks. And yeah, we've trained a model for you. We've given you just the model weights, but not what the original training data set was. And then, yeah, you have to go and implement this attack. And then, yeah, there's an evaluation function you can use which will cheat and use the ground truth information to figure out how well your attack did. Yeah, question?
Yeah, like step one, the third part, it says like to guess a model. It's
Yeah.
basically like just like a hyperparameter, I'm just guessing like intuition, or is there like a smart way to do it?
Yeah, so the question is, step 3 here is guess a model. How do you do that? Is it just like a parameter of the attack and you have to just pick one yourself, or is there a smarter way to do it? So there's a lot of research on this topic. There might be slightly better ways to do it, but for the purpose of today's lecture, it's like use your intuition, figure out what kind of a data set the original model was trained on and like roughly what kind of an architecture it has, right? Like if it's an image data set, then maybe you guess some sort of CNN architecture. Or if it's a tabular data set, like probably not a CNN, right? Yeah, there's also all this literature on model stealing. You might also be interested in looking that up. I have a couple links in the lecture notes. And there the setup is, yeah, I guess the thing we talked about originally, or a little while ago, where there's a model available for black box queries and you're trying to infer the model architecture and parameters. Yeah?
What is the separation of D in and D out? And how does that correlate to yes and no, it was trained in the data set?
Okay, so the question is, what is the separation of D in, D out, and how does that correlate with what's in the data set and what's not? In equals yes, out equals no. I kind of switched notations halfway through. But the whole idea is to train the model A, you need positive and negative examples. That's the most straightforward way to train it. And so you're just going to synthesize that yourself. Like have examples you're going to train on, and then have other examples you know you haven't trained on. And then that way you can evaluate your shadow model on the things you trained on, and then label that, yes, that was stuff I trained on. You evaluate it on the stuff that you didn't train on, the D out, and then you label that as, no, I didn't train on this. And that's how you get your binary classification data set.
So you train M shadow on D in. Okay.
Yes, you train M shadow on D in. I kind of abbreviated some of the notation for the Blackboard. The lecture notes have slightly better notation, so you can also refer to that later. Cool. So this is a pretty recent attack. This paper came out in 2016 that proposed this attack. I think that was the first time people really thought about membership inference attacks on deep neural networks. So yeah, fairly cutting edge research. So any questions about this attack? What are some of the downsides of this attack? What's not so appealing about this? Yeah.
The assumption that like the prime has to be similar to D.
Yeah. You can start writing these down. Downsides of this attack. It assumes that you can find some D prime that's similar to D. Any other things that are not so appealing about this? Yeah.
Like the original model may be very complicated, so it may cost a lot of money to actually train the M shadow.
Yeah, the original model might be really complicated, and so it might cost a lot of money to train M shadow. So yeah, you're right, this is computationally expensive. Yeah, I think those are some of the main ones. Yeah, it's very expensive. It's also kind of complicated. Like, it took me a while to explain. It's kind of annoying to implement. And so there's been some follow-up research on a very different style of membership inference attack. This one is called a metrics-based attack. And basically, these attacks don't do all this upfront computational work. Instead, they do simple things like just feeding the data point to the model, getting the output prediction vector, that y hat, and computing simple metrics based on that. And actually, before I tell you what some of these attacks look like, can anybody just figure it out on their own? Like, they're actually pretty intuitive, I think. Someone might just be able to guess what these attacks might look like. So I have a data point, I can feed it into a model and get a prediction vector out. What might be one way I could identify whether that data set was included, or that data point was included in the model's training set? Yeah?
You can see how confident it is in like all the positives.
Yeah, exactly. You can see how confident the model is about its output. So one example of a metrics-based attack is looking at confidence. So the attack just takes in, okay, you have your x, you compute y as m of x, and then the score is just the max of this output vector. How confident is the model in its output? And what's interesting, so I won't go through a whole bunch of metrics, like they're more in the lecture notes if you're interested, but here's what one of them looks like. And yeah, what's kind of interesting is that this works pretty well. Some intuition for this is just that when you train a model on a data set, like the loss functions that we commonly use cause the model to be very confident in the outputs it's predicting, right? And so usually the models are pretty good at remembering or doing well on their training set. Oftentimes you can get the loss very close to 0. And so if you just feed in a training data point, you might have a prediction vector that just has a very high score for a single label. Whereas on test data it hasn't seen before, it's sometimes a little bit less confident. And so you can compute a score that way. Did anybody notice the slight mismatch between, like here we were getting a yes or no output, and here we have a score? Yeah, so there's an additional step required here. You need to choose some sort of a threshold, and then decide or label or form your answer as yes or no based on whether your score is less than that threshold or not. And then there are some details here, like how do you choose that threshold? And maybe things like knowing the model's average confidence on test data or training data or something like that might be helpful. But yeah, there's some extra details there that are a little bit tricky to get exactly right. Cool. Any questions so far? Yeah? I can't hear you.
Should it be greater than? You're saying like if it's 1.0 to 1.3.
Yeah, you flip the yes and no. But yeah, you're thresholding based on some threshold, and assign the yes and no appropriately. All right, so let's wrap up with these membership inference attacks. I'm going to briefly talk about another kind of really interesting attack called a data extraction attack. So it turns out that machine learning models and neural networks often unintentionally memorize parts of their training data. And so based on that, there are techniques for trying to extract some of this training data from a model. So yeah, this attack just involves, given a model, just try to figure out what was a data point used in the training set. So a little bit different than membership inference, because we don't start with a data point here. We have the data set D that we have a model M train on, and then the attack is like, just given M, we want to find some X that's from this training data set D. The one interesting example is data extraction attacks on large language models. So you've heard of things like ChatGPT or GPT-3 or OpenAI Codex or GitHub Copilot, right? These things are huge, like many billion parameter models trained on huge data sets, and sometimes they might even be trained on sensitive data. Like you could imagine, say, GitHub Copilot-like system being trained on private GitHub repositories. I don't think they actually do this, but you can imagine them doing so, right? And if you could extract parts of the training data, that could be problematic, right? Like people sometimes check in private API keys into their private GitHub repos. And so if you could somehow coerce the model into giving those back to you, like that's revealing sensitive information that should not be revealed. And you can try playing around with some of these models like ChatGPT, and one way to try to attack these is just with prompt engineering. Like you'll feed in something like, my social security number is, and ask GPT-3 to complete that sentence for you. And if it's seen anything like this, then it's going to be pretty likely to output something sensitive here. So that's one way you can do it. And then I'll briefly sketch another really interesting attack. I don't remember if this attack has a name, so I'll just write down the author's name. So this other attack involves 2 steps. It's pretty simple. Step 1 is just sample a bunch of data from the model. So is it clear what I mean when I say that? Like we have a language model and we sample a bunch of data from it, or should I walk through how that works? Raise your hand if you want me to walk through it. Okay, yeah, I'll briefly talk through it. Maybe I won't draw too much on the blackboard. So at a high level, these language models are trained on sequences of text. And here I'm simplifying things a little bit, but basically what they're trying to do is, given a sequence of characters, they predict a probability distribution over characters for the next character they think is going to appear in the sequence. So like they're trying to predict p of, say, xi, the ith character, given x1 through xn. It's trying to learn this distribution. And so if you want to sample from these models, like basically the way you do it is you start with a start of sentence token, and then you just basically in an autoregressive fashion keep sampling from this probability distribution. So you'll feed in your just start of token and then sample the next character. Then you feed in your first two characters and sample the next character and so on. And so you can just do this a whole bunch of times and get a bunch of different sequences. All right, so now you have a bunch of sequences sampled from the model. And then step 2 is going back to what we talked about before, do a membership inference attack. Because step 1's going to generate a whole bunch of stuff. It doesn't necessarily mean that it came from the training set. But in step 2, we're going to figure out which of those things were in the training set, right? Like that's exactly what a membership inference attack does. And in this particular attack, we're not going to do something so fancy like training shadow models. There's actually a pretty straightforward metrics-based way of doing this for language models. And basically, you can use as a score, use this thing to basically look at the likelihood that the model would generate that particular sentence. Using, this is called perplexity. You can actually write out the formula for that. Right, so this is what our language model is capable of producing. And what we can do is compute this quantity here. Basically, we're going to look at all these different probabilities and sum them up. Log p of xi given x1 through xn minus 1. And that's pretty much it. And turns out that if you do that with a couple extra clever tricks added on top to get higher quality results, you can actually extract real training data from these large language models. So when these authors did this research in 2021, they were attacking GPT-2. I guess that was the latest and greatest transformer model available at that time, perhaps. And they found that they could extract hundreds of memorized training examples from GPT-2. They actually confirmed this with the authors, so they have the ground truth there. So that's pretty cool. Yeah, so any questions about that? Yeah.
In case of images, you don't have a training set to start with first. Let's say it's not so clear that it's cat and dog or something weirder. Have there been examples of using, could you compute gradients, I guess, on the score metrics and then just sort of generate fake data towards that or something?
Yeah, so is the question how you do this kind of a data extraction attack against image models?
Yeah, I guess.
Yeah, so actually, yeah, what you described is pretty close to what people do. So yeah, there are ways to use very different attacks than this one shown here, but there are ways to attack image models and image classification models, which are very different from these generative models, right? Yeah, there's research on that. I won't go in detail on that in this lecture, but I can talk to you afterwards if you want links to those. But yeah, at a high level, you can chain together a couple of things, use generative models trained on data that looks roughly like what you might have used in the training set of the model, and use that to help find or reconstruct some of the input data. Cool. Any other questions? Right. There was some other material I was considering talking about, but I think I will wrap it up here. At a high level, this is still an active research area. It's an unsolved problem, and that there's no like be-all, end-all solution to it. There's some promising directions. It's actually really hard to do research in this area because you might propose like reasonable sounding things for defending against these kinds of attacks, right? Like maybe going back to membership inference, you might say, okay, before in this shadow model attack, we were using the output of the model there, that y-hat, and maybe one plausible thing to do is maybe our API can just add some random noise to that vector. Like that seems like a reasonable thing to try, right? Like maybe that'll throw off the attacker. But it turns out that a lot of these kind of empirical solutions don't really work. And when you evaluate them the right way, going back to what we talked about earlier, how a system or like a defense is only secure if it's robust against all possible adversaries that follow the threat model. If you really analyze them in that way, it turns out that a lot of these empirical solutions don't really work. Like for example, yeah, people have proposed adding random noise. Turns out that you can just call the model a bunch of times and average the predictions, and you've gotten rid of your random noise, basically, right? And there are a lot of other things, like you could quantize the model outputs. Like instead of giving 32-bit floating point output, maybe you could only give like 16-bit floats or 8-bit floats, things like that. Turns out that those things don't work too, and there are clever ways to work around that. You might think that a model that only outputs, say, a sorted list of classes rather than the predictions themselves might be robust. Turns out there's ways to attack that as well. And yeah, this just goes on and on and on. And so if you're ever doing work in this area, or if you're ever looking at defenses and trying to think critically about whether or not they're reasonable, like you need to think really hard about, okay, like did whoever proposed this defense evaluate it really thoroughly? Did they really try like as hard as they could, thinking in the minds of the adversary, to break their defense and fail to break it under their threat model? Because yeah, usually our threat models are broad enough that we can't actually like computationally evaluate all possible attack algorithms over my defense. And so the way these things end up being evaluated is we just try really hard to break the defense, and if we fail, then we think like, okay, the defense is probably reasonable, publish a paper and maybe somebody comes along and breaks it next year. But yeah, that's how evaluation works. It's actually really hard. This is an unsolved problem. And yeah, with that, are there any questions on data privacy and security? Yeah.
Like, what's the common practice in companies now? Are they doing any of this stuff, or are they just like coming up with like a block list of lists that people can't search lists, or like a limited number of queries?
Yeah, that's a great question. The question is, what are companies doing about this right now? Like, what's the real world solution today? And I don't have perfect visibility into this, but I think at a high level, what's going on is people aren't too worried about this. Like maybe once it becomes more of a problem, people will start worrying about it more. But that's part of the solution. There are some people who are deploying certain techniques to, say, build more robust models. And one thing we didn't talk about today was something called adversarial examples. Like it turns out that you can craft like carefully tuned inputs to machine learning models that basically allow you to control the output. So you can say, given an image classification model, give it a picture of something that looks like a cat to you and me, but the machine learning model thinks it's a dog or a guacamole or something totally random. Like you can control it, even though, yeah, the image looks like totally normal to humans. And so like for that particular problem, for example, there are some companies who are using what's called adversarial training, which is one defense against that sort of an issue. And they're actually using that on deployed models. And for some of these other attacks, yeah, so in addition to these kind of machine learning-based defenses, actually making the model more robust. And again, thinking about things in a more system-oriented way, and thinking about like what other safeguards can you put in place to prevent these types of attacks. So like for some, there are some attacks against machine learning, so like not these ones we talked about today, but there are some attacks that are very like query intensive, for example. And so someone might set up an ML model such that it, say, does rate limiting and only allows 10 inferences per IP address per day. And then like maybe that's good enough. But yeah, so it's a combination of techniques that are being used today. Any other questions? Right, cool. Well, that is all I have on data privacy and security. And with that, that's actually the conclusion of our introduction to Data-Centric AI IEP class. So we hope you enjoyed it. And then all the lecture material, notes, videos, labs, everything will be available online afterwards. Yeah, we'll stick around for a little bit to talk to anybody who wants to talk to us. Cool.